How's it going, ladies and gentlemen? Mr. Donahue here once again. This time we're going to take a look at 6.4 stuff, wave behavior of matter. So we're going to start with number 16. It says, briefly summarize the Heisenberg uncertainty principle in your own words. So for me, how I would put it in my own words, it's pretty much the more you know about where a particle is, the less you know about where it's going. You can't know either with absolute certainty. So like, one analogy is you're taking a picture. Let's say you're taking a picture of a car, and this is my excellent car. If you that's a car, just bear with me, all right? That's a car. There's a door. All right, if you took a picture of this car, well, now I know where it is, but I don't know if it's moving, right? Whereas if I had like a longer shutter speed, it might have a blur where it looks like that car is moving, and I can tell you where it's going, but I know less about where it is because it's all blurred. So the more you know about one, the less you know about the other. All right, 17. The de Broglie wavelength of which object will have the shortest wavelength when they're all traveling at the same velocity. Well, the formula for the wavelength, for the Broglie wavelength of objects is the wavelength equals Planck's constant over the mass times the velocity. So they're saying if the velocity is kept the same, which one will have the shortest wavelength? So we're looking to decrease the wavelength. We want that to go down. Well, how do we do that? Well, h is a constant, and they're saying velocity is a constant, so we are messing with mass. So it's going to have to do with mass. And if I want a smaller wavelength, I want a bigger mass because it's in the denominator. So I'm looking for the thing that has the biggest mass, and we got a thimble, the Earth, a helium atom, a bus, and a baseball. So definitely the Earth. It is the biggest thing there. 18. What is the Broglie wavelength in meters of a 3.0 kilogram object moving at that speed? So again, I know that the wavelength equation is going to be equal to Planck's constant over the mass times the velocity. So now I just plug it in. I go, all right, well, I know h is 6.626 times 10 to the minus 34 joule second, all over 3.0 kilograms. And I need it to be in kilograms because, like, when we're talking about what units are actually joules, it's in kilograms. So kilograms times the velocity of 40 meters per second. And what I end up getting is a wavelength of 5.5 times 10 to the minus 36 meters. So pretty small wavelength, right? If we're talking about light, it's usually in the 10 to the minus 9 meters. This is 10 to the minus 36, so it's a lot smaller than a wavelength of light, which is why you probably wouldn't even see it, wouldn't be able to tell. All right, so 19 says, what is the de Broglie wavelength of an electron that has a velocity of this? And it tells you the mass of the electron. And this should be, meters per second. Oops, sorry, I didn't put the units there. So let's do this math again. So we want the wavelength, and it's going to be equal to Planck's constant over the mass times the velocity. So again, 6.626 times 10 to the minus 34 joule seconds, all over the mass, which is at 9.11 times 10 to the negative 31 kilograms, which is given right here. And then times that by the speed or the velocity, which is 6.00 times 10 to the 6 meters per second. And when I plug and chug and get that, I get 1.21 times 10 to the minus 10 meters. So this is, again, small, because if we had nanometers, it's usually 10 to the minus 9. This is 10 to the minus 10. So when we use moving electrons to look at things like in an electron microscope, we have a higher resolution because its wavelengths are smaller. All right, so I think that's it for that section. Hope you found it helpful. See you in class. Okay, bye.